All right, this video cast, we're going to talk about how to draw Lewis structures and especially incorporate those multiple bonds, and we'll finish up our topic on covalent bonding. So with Lewis structures, we use a line to represent a bond or a shared pair of electrons. So always remember to count a line as 2 electrons. The central atom is carbon, or the least electronegative atom. It is usually going to be the first one written, unless the first one written is hydrogen. Hydrogen is never the central atom because it can only make one bond. And so if it's the first thing written, it is not in the center. So we can do little things like, if I have a compound, let's draw methane, CH4. You're going to start with your center atom. Our center atom here is going to be carbon because carbon's always in the middle. So we write carbon. How many valence electrons does carbon have? And you'll need to consult the periodic table for this. How many? 4. All right, good, because it's in group 14, and you just drop the 1 off the front or subtract 10 from it. So 4, 1, 2, 3, 4. All right, you can't make up your own dots. That's how many you can put on there because that's how many carbon has, how many valence electrons it has. Now, we're going to attach 4 hydrogens to that. How many valence electrons does hydrogen have? 1, because it's in group 1. Hydrogen comes in with its 1, and then we're going to form a bond. Another hydrogen with its 1, and then they bond. Another hydrogen with its 1, and they bond. And another hydrogen here, and they bond. Then you're going to check to make sure that everyone is happy. And we're going to follow the octet rule, the things we're going to draw. Everybody wants 8 except for the little guys, and hydrogen is a little guy. Let's look at carbon first. Remember, you're going to count each of these lines as 2 electrons, so you can count by 2s or count either end of the line. So we've got 2, 4, 6, 8. For carbon, so it has access to 8, so it's happy. And each hydrogen has access to 2, and he's a little guy, and he's happy with 2. So this is a nice, happy, stable molecule. Everybody okay with that? All right. Let's see. Now we're going to talk about sometimes just by making single bonds, they cannot get to a state where everyone has access to 8 electrons. They end up having to share more than a single pair of electrons. So we're going to talk about multiple covalent bonds. So these would be double and triple bonds. The more bonds you have, the higher the bond dissociation energies, which just means stronger bonds. The stronger the more bonds there are, the stronger they are, and the shorter the bond lengths are. So, a double bond is stronger than a single bond. It takes more energy to break that double bond than it does a single bond, just like it takes more energy to break 2 sticks than 1 stick. Okay. Also, the more electron pairs that are sharing, the closer the atoms get to each other. So, if we have a single bond like this, as we share more electrons, the atoms get closer together. Right? So, our double bonds are stronger than single bonds. You especially have to watch out for carbon, nitrogen, and oxygen. They will often double bond. Or, if we take the symbols for each of these, they con double bond. Okay, come on, that's cute. Right. And then triple bonds are the strongest. They're also the shortest. And carbon and nitrogen will often triple bond. Now when we're drawing these, I want to show you how you know if something needs to have more than one bond. And we're going to start with a nice stable compound that we're all producing right now, so we know it exists, carbon dioxide. What's going to be in the middle? Carbon. All right. Carbon has how many valence electrons? How many? 4. All right. Good. All right. So carbon has its 4. Now I'm going to, we've got 2 oxygens that are going to bond to this carbon. I'm going to put 1 oxygen over here. How many valence electrons does oxygen have? 6. Good, because it's in group 16. We just dropped the 1. 1, 2, 3, 4, 5, and 6. I always put 1 out there because I know we need to make a bond. And we'll do that. And we're going to find if 1 oxygen is on one side, the other one's going to try and be as far away from it as possible. So we'll put it on the other side. It also has 6 valence electrons. And then we bond. Then you look to see if they're happy, because remember, that is the reason why atoms are going to bond, is to become more stable. And if they can't become more stable and have access to 8, they are not going to bond. So oxygen has access to 1, 2, 3, 4, 5, 6, 7. Is he going to be happy with that? No. Carbon has access to 6. Not happy. Nobody's happy in this situation. So what's going to happen is an electron from oxygen and an electron from carbon are going to come together and form another bond. Now, drawing these Lewis structures, it's going to be less irritating if you do it in pencil, because sometimes you do have to erase, and pen can just get kind of messy. Now, when you bring those arrows up, or bring those electrons up, you do not have to write those arrows. I did that for effect's sake, but make sure that you go back and you erase those electrons, because they are now participating in a bond. So now, is this oxygen here on the left, is it happy? Does it have access to 8? Yeah, 1, 2, 3, 4, 5, 6, 7, 8. So it's happy. What about carbon? Is it happy? No, it has access to 7. You just pissed it off. So what's going to happen? It's going to make a bond with the other oxygen. So this electron's going to come down, and this electron's going to come up, and they're going to make another bond there. So we end up with 2 sets of double bonds. And again, I just made it hard for myself to erase. There we go. That is the structure for carbon dioxide. You can now see that everyone has access to 8. That makes it a nice stable molecule. Everybody okay with that? All right. I'm going to give you some to try. Now, be careful. Sometimes I get students and they get to this point and they don't have 8, so they just put more dots. Remember, these represent valence electrons, and you cannot just make an electron just by wishing that there was one, like, I made an electron. No. No. All right? You have to go with how many electrons the atoms actually have when you're drawing these. All right, so let me give you some. He's a little bit of a challenge. Let's give it a shot. Okay, so I'm going to now, you should try and work these problems. If not, pause the video cast and work them, and I'll show you how to draw them in just a second. All right, so we have sulfur. Sulfur has 6 valence electrons, 1, 2, 3, 4, 5, and 6. And then there are 2 hydrogens that are going to be attached there. Hydrogen can't be in the middle, so that's why I started with the sulfur. Each hydrogen comes in with 1 valence electron, and they're going to bond. Now, at this stage, yours probably does not look exactly like mine, but a lot of this is about exposure. It's just going to have you've never seen molecules drawn out like this. But the more you see them, the better yours are going to look, as long as you end up here. And what we call these right here are called unshared pairs. So you end up with 2 unshared pairs or lone pairs on sulfur, and then 2 bonds, 1 to each hydrogen. All right, then we're dealing with B. We have silicon. You just have to be careful and not confuse the dot on the I with a valence electron. Silicon's in group 14, so it has 4 valence electrons. And then we have 4 bromines that are going to bond to it. Each bromine has 7 valence electrons, 1, 2, 3, 4, 5, 6, and 7, and then we'll bond. 1, 2, 3, 4, 5, 6, 7, and then bond. This bromine, 1, 2, 3, 4, 5, 6, 7, and bond. And 1, 2, 3, 4, 5, 6, 7, and bond. Now we have this complete structure. You look and make sure everybody has access to 8. This bromine has access to 1, 2, 3, 4, 5, 6, 7, 8. So all the bromines are happy, and silicon has access to 1 or 2, 4, 6, 8 as well. Up here, I didn't talk about with letter A. This sulfur is happy. It has access to 1, 2, 3, 4, 5, 6, 7, 8. And each hydrogen, because he's a little guy, is happy with 2, and they both have access to 2. Then we get to oxygen. It's 2 oxygens bonded together. One oxygen has 6 valence electrons, 1, 2, 3, 4, 5, and 6. Then I'm going to have the other oxygen over here, 1, 2, 3, 4, 5, and 6, and that way I can bond them. And then I count to see if they're happy. Now each oxygen has access to only 7. So what's going to happen? Double bond. This electron's going to move up, and this electron's going to move up, and they're going to create that double bond. And this is the oxygen that you breathe. It does have a double bond there. Again, go back and make sure that you erase your electrons. Okay, I don't know why that one keeps appearing. So then we have N2. So I have nitrogen, which has 5 valence electrons. And I often will put my 5 valence electrons like this, where I have 1, 2 at the top, and then 3, 4, and 5 there. Going to bond to another nitrogen, 1, 2, 3, 4, and 5. Then they're going to bond. And then we check to see if they're happy. Each nitrogen now only has access to 6. So electrons are going to move up, 1 from each one, and create a double bond. Then we check to see if it's happy. And each nitrogen only has access to 7 valence electrons. So again, not happy, so don't stop until they're happy. This electron and this electron are going to move up, and they're going to form a triple bond. So N2 has a triple bond, and that's not terrible information to have in your head, just that nitrogen is a triple bond and oxygen gas has a double bond. The little challenge problem, the reason why they separate out these hydrogens is because these 3 hydrogens belong to carbon and these 3 hydrogens belong to nitrogen. Now we will have to link all of these up together because it is one molecule. This is methylamine. So we've got a carbon. It has 4 valence electrons. And we have 3 hydrogens that are going to bond to it. So each hydrogen is going to come in with 1 and form a bond. And then we're going to attach the nitrogen to the carbon. Nitrogen has 5 valence electrons, and they're going to bond. And then 2 hydrogens on that nitrogen. So each hydrogen comes in with its 1 and bond. And that's what that little molecule looks like. Did you do okay? All right, just remember you can't make up the number of dots, and you have to be very careful to erase them, especially when you have situations like this where you end up with double or triple bonds. I'm going to give you some more practice on your homework in writing those or drawing some more structures. Okay, now we'll just kind of finish this up. I'll go just a little bit higher here. All right, we're going to talk about resonance structures. This is one of those situations where we named something before we actually knew how it really worked. When I say that my voice resonates in the room, what does that mean? Louder and like an echo almost, yeah? All right, so with resonance structures, we thought that we had like bonds that would bounce between, and they would echo or bounce between atoms. And that's why we named them resonance structures. But we've since found out that that's not the case. It's actually a blend of structures. But the name had already stuck, so we're stuck with it. Like, I know an adult male who goes by Squeaky. Yeah, I do, for real. His name is Squeaky. He when he was a little kid, when he was a baby, he squeaked a lot. And so his parents called him Squeaky, and the name stuck. And that's everyone. No one knows his actual first name. Like, everyone knows him as Squeaky. It's just how it is. I went to high school with a kid named Ugg. He was not ugly, as his name might imply. He was quite beautiful. But he, when his little brother was born, his actual the guy's name is actually Greg. But when his little brother was born, was learning to talk. He couldn't say Greg, and it came out Ugg, and it stuck. And so he just kind of kept it forever. But it was kind of cool. Ugg was in a band with a guy named Eck, so it was Eck and Ugg. Okay, but a resonance structure resonance structures are compounds that cannot be represented by a single Lewis structure. It takes more than one to explain their structure. The example I'm going to give you is ozone. Ozone is O3. And this is what protects us from ultraviolet radiation is in the form of the ozone layer. We made a giant gaping hole in it with some of the cool chemicals we found in the 70s. But we've stopped using those, at least here in America, and it has shown signs of closing back up. Not completely, but it is getting smaller. But it's pretty serious. With that ozone layer gone, the hole was kind of over Australia. And there would be days in Australia where they would say, do not go outside with exposed skin, because there is nothing protecting you from the sun's UV radiation. Nothing. All right, so pretty serious stuff. But when we draw ozone, either one of these Lewis structures does not accurately explain the structure of ozone. We thought that this double bond kind of flipped and flopped back and forth, but what we found is it's actually a blend of these two structures. And it's like each oxygen has a bond and a half. Well, our drawings aren't that good, so what we end up doing is drawing all possible structures that kind of average out to make the blend with a double-headed arrow in between. At this level of chemistry, you just have to know what a resonance structure is. When you get into AP chemistry, then we start drawing all the structures. Ozone has a pretty distinct smell, too. It's like after a lightning storm, or if you have like an ionic air purifier, it has a certain smell to it. That smell is ozone. And it's a ground level pollutant. Oddly enough. Okay, here is my weak joke for today. Network bonding. It's what you do on the computer late at night. Okay. That's all right. That's about as much laughter I got all day. Again, we're still talking about covalent bonding here. And if with network bonding, the bonding occurs in 3 dimensions, forming these networks. Ionic is stronger than covalent if we just look at them at face value. But when covalent bonding happens in these 3-dimensional networks, they end up forming stronger overall bonds than ionic. You don't have to draw that. I just wanted to show you what it looked like. Silicon is a network solid. Diamonds are network solids. I always thought it's kind of weird that your pencil lead and a diamond are made up of exactly the same thing. Exactly the same thing. It's just the way that they're bonded that gives it the difference. Good. Yeah. Yeah, absolutely. Probably take some time too with that one, but yeah, we can make synthetic diamonds. They're talking about making it out of remains now too.
I saw that.
Yeah, where you could. Yeah.
Jesus.
I guess you could do it that way. All right. That's as far as I'm going to go with this.